Welcome back to Applied Physics. In this video, I want to talk about Hooke's law. Hooke's law is the mathematical model for discussing elasticity. Elasticity itself is the property of materials that when you deform them in some way, they tend to come back to the shape that they had been in the first place. The classic example of elasticity is a rubber band. If you grab a rubber band and you stretch it and you let it go, it will return to roughly the same shape that it was in before. If you move it around and don't put too much stress on it, right, the friction between the rubber band and the table that it's resting on is enough to hold it in place, but as soon as you apply some stretch to it, it will come back, and if you let it go, well, the force of it returning can cause some utter mayhem. I'm going very blurry here. I don't know what's happening. Let's try rebooting that camera. Somehow that often tries to fix things. But here I have another object that exhibits a more interesting behavior in deforming it. Let me get my head out of the way because I actually need all of my hands and I can't look at my camera while I'm using all of my hands. But if I deform this bit of wire by a little bit, then it's going to bounce back to where it was, giving us a nice elastic deformation. If I bend it too far though, it will kind of give up. And so I can bend it in a way that it does not retain its shape or it's a new shape. That's called a plastic deformation. In material science, plasticity is the willingness of a material to take on a new shape. The household material that we commonly refer to as plastics are shapes that are, or materials that are interesting and useful because we can get them to a certain temperature, at which point they will take on whatever shape we push them into, such as through a vacuum mold, and then when they cool off, they will retain that new shape. So we can plastically deform this material quite readily, hence plastics. The property of elasticity measures how well a material can handle this sort of a deformation. And the place where we're going to find it most useful to think about is in the application of working with springs, right? I have here a Slinky, a wonderful toy that is great for talking about springs because it exhibits exactly that elastic behavior. If you deform the spring by a little bit, it will bounce back into its original shape. It will tend to overshoot and then have to redirect itself, and there's some interesting things that can happen with that. But the general property of a spring is the thing that we are most interested in. The mathematical formulation Hooke's law models the behavior, I should have an extra word in there, models the elastic behavior of what we refer to as linear springs. This is one of those definitions that is so simple and so stupid, and it's a wonder that it is useful at all. Hooke's law models linear springs. A linear spring is a spring that behaves according to Hooke's law. So yeah, not all springs behave this way, and not all springs behave this way for the entirety of their possible behaviors. If you've ever played with a slinky, you know that at some point somebody is going to overstretch the slinky and it never quite comes back to its original shape again. That overstretching is escaping the linear elastic behavior that is the definition of Hooke's law. But for most springs, for most applications, we can use Hooke's law and we can use it quite effectively. Essentially, if we design a system using a spring well, we use the spring only in the part of its behavior that does obey Hooke's law, and we make sure that the application has enough of a leeway that if it exceeds the expected environment, it will still behave under Hooke's law for a reasonable or perhaps unreasonable, depending on what kind of engineering you are doing. All right, so enough talking about how to talk about Hooke's law. Let's actually write down Hooke's law. Hooke's law tells us that the force generated by a spring is equal to the negative of K times S, where K is called the spring constant. You'll see some sources that call this the spring stiffness, the stiffness constant, or just the stiffness of the spring. But the usual definition for a physicist is we call this the spring constant. The spring constant is a property of the particular spring, and it describes how stiff the spring is. I apologize, this is going to be a very bright screen. Actually, no. Let me turn on my color inverter, and then we can stick with a dark spring and look at this. The shadows look a little bit weird, but other than that, it mostly makes sense. All right, so here we have a spring. We have a device whose purpose is to grab the spring and try to move it, and that's all that we have going on. And let's move this over here so it's a little bit easier for me to point at things. There we go. All right, so we're going to apply a force. You can see currently there is no force being applied on this spring, but I can apply a force in the negative direction. Maybe I can apply a force in the negative direction. There we go, now I'm actually clicking on the right thing. We can apply a force in a negative direction, which causes the spring to compress. You can see that when I applied this force, it pushes the spring away from that equilibrium position. Right? The blue dotted line here is the position where S is equal to 0. We have moved inward from it, so we've moved in the negative direction, which means that the spring wants to push us back outward. The spring force is going to be in the positive direction. If instead of pushing on the spring, we had pulled on the spring, then the spring instead wants to push us or pull us back to equilibrium, right? We have displaced the spring out this way. The spring force is trying to pull us back. The negative sign is telling us that the spring force is always moving in opposition to how we are pushing or pulling the spring. The spring constant gives us a scale of how much force that is. You can see down here I currently have a 300 Newton per meter spring constant. If I drop that down from 300 to 100, well, now there is less force trying to overcome the spring, and so the spring is pulled even further. If instead I had a very high spring constant, well, the force is greatly exceeding the force by which we are pulling on the spring, and our pulling the spring is barely doing anything now. So the spring constant tells us how much the spring is trying to overcome or resist the pull of that force, and we can always have that spring spring force in opposition to the direction that we're trying to move the spring. Let me get back to my notes. Let me get my head out of the way, and let's look at a particular example. A force of 12 newtons is enough to stretch a spring by 8 centimeters. How much force is necessary to stretch this spring by 12 centimeters instead? There are several ways to approach this problem. The approach I'm going to use is not necessarily the easiest mathematically, but it's the one that should be the easiest conceptually. I'm going to break this problem into two parts. In the first part, I'm going to use the known information to determine the spring constant. The known information is this first sentence. If we apply a force of 12.0 newtons, then we stretch the spring by 8 centimeters, which is 0.0800 meters. I could have left everything in centimeters, but I'm not going to. The last thing we need is an assumption that at this point the spring is in equilibrium. Right, so we have a spring. We are grabbing that spring and putting some applied force on it. The spring is pulling backwards. There is probably also gravity pulling downward, and the spring is in some sort of a support which is preventing it from falling downward, and that support is providing a normal force. In the y direction, the normal force and gravity are going to cancel each other out. None of that is useful to us. In the x direction, it is useful to us to know that Fa plus Fs, which is the net force in the x direction, has to be equal to 0. So from that, I can say that Fs is the negative of Fa. I said that I wanted to find the spring constant. To find the spring constant, I need that formula for Hooke's law. Fs is minus Ks. The negatives will cancel each other out. I can also divide both sides of the equation by s to get that K is Fa divided by s. Fa is 12.0 newtons, s is 0.0800 meters, and when you punch that into a calculator, you get 150. I'll put a decimal point at the end because that 0 is significant. And my units here are in newtons per meter. Very often when a student first sees those units of newtons per meter, I get the question of, well, can't we reduce that? Remember, a newton is a kilogram a meter per second squared, so the meters could cancel each other out, and this unit is equivalently kilograms per square second. But when you think about conceptually what is happening here, The spring constant is the rate of proportion between distance and force. So the units as a distance and force, as a rate, newtons per meter, makes the most sense. We'll leave them like this. We won't try to rewrite them in any other form. The important thing, though, is that we now have our spring constant. So with our spring constant, we can continue onward. Step 2. Is to finish the unknown situation. We now know that our spring constant is 150 newtons per meter. In the unknown situation, we were given that the spring is stretching by a distance of 12 centimeters, 0.120 meters, and then it is the applied force that is the unknown. We start off the same way that we did before. With our free body diagram, we know that Fa plus Fs has to be equal to 0. Since we're solving for Fa, we'll leave that alone on the left-hand side. Hooke's law tells us that Fs is negative Ks. That is a double negative. Negative of a negative in mathematics is a positive, so this is just the spring constant times the distance. Our spring constant is 150 newtons per meter. Our distance is 0.120 meters. And when you punch that into a calculator, you get 18.0 newtons, right? The meters cancel each other out, leaving you with newtons. And so we can conclude that it will require 18 newtons of force in order to stretch the spring by a distance of 12 centimeters. As springs go, this is a fairly sturdy one. There are certainly applications where that is important. There are certainly applications where you want a much lighter spring. The last thing I'm going to say before we wrap up is it is amazing how many things can be modeled as linear springs. Springs do not have to look like a slinky with the coils of wire that are jumping up and down. A leaf spring is something a little bit closer to that little bit of bent wire that I was looking at before, where this one has a very, very small spring constant, but you can get them to be stiffer. You can also model things that are not spring-shaped at all. Right? A steel beam, in a lot of senses, is a spring. If you're applying forces to a steel beam that might cause the beam to deflect or compress or stretch, it's going to behave as a spring within at least some regime of possible forces. One of my favorite applications of springs is in electronics. An RC circuit, well, not an RC circuit, but an RCL circuit with a resistor, a capacitor, and an induction coil. The electricity in the circuit acts as though it is caught in a spring. Mathematically, the model is exactly the same. And in fact, the circuit diagram icon for a induction coil looks like a spring, in at least part because of that inspiration. We can also think about springs in chemistry. A chemical bond between two atoms can be thought of as a spring force trying to keep those atoms together, and as you stretch them out, they're going to bounce back and they're going to oscillate following the behavior of a spring. So springs are everything. Everything is springs if you stop and think about it long enough. But for now, I think that's enough for this video. So thank you as always for joining me. I'll see you next time.